are provided with solution A, a mixture containing sodium thiosulfate and starch. Solution B, aqueous potassium iodide. Solution C, aqueous hydrogen peroxide. Solution D, 0.1 m potassium manganate 7. You are required to determine the concentration of solution C and the rate of reaction between hydrogen peroxide and potassium iodide. So procedure 1. First, before we go to procedure 1, whenever you see 0, whenever you see, for example, 0.01 capital M, this means number of moles in 1,000 centimeters cube of that solution. That's what it means. Using a pipette and a pipette filler, pipette 25 centimeters cube of solution C into a 250 ml volumetric flask. Add distilled water to the mark and label the solution E. Fill the purity with solution D. Remember, solution D is potassium permanganate. Using a clean pipette filler, place 25 of solution E into a 250 ml conical flask. Titrate with solution D until a permanent pink color persists, and then fill the table. So nataka uone kwamba we are pipetting so aqueous peroxide. We are taking 25 of hydrogen peroxide and then we are diluting it in a 250 ml volumetric flask, forming a solution E. From C we form E. So the volume, I'm going to give the figure. So make sure you fill the table with 1 decimal place or 2 decimal places consistently. Don't mix. So determine the average volume, solution D, the average volume. Now we have 16.9 plus 17.0 plus 17.1 divided by 3. This gives us 17.00 centimeters cube. The average volume is usually given in 2 decimal places. Calculate or determine the number of moles of potassium manganate 7 that reacted. Remember, manganate 7 is solution D. This one is solution D. So solution D, the volume is this, and it reacted with solution E that we diluted. But what do we know about manganate 7? What do we know with solutions? We know that the molarity of solution D is 0.01 mole, meaning the number of moles in 1,000 we know. 0.01 is the number of moles of D, solution D, in 1,000 centimeters cube. Now we would want to find out what will be the number of moles of 17 centimeters cube of the same solution. What will be the number of moles? This means it is 17 times, we go this way, 0.01, we divide by 1,000, and this one will give us 0.00017 moles. That is the number of moles, or you can use the formula moles. When we want moles, because we have the molarity, and then volume in liters. So we want moles. So moles is equal to moles. You stand here, it is equal to molarity times volume in liters. Our molarity is 0.01 of solution D, and the volume in liters, the volume that we used was 17. 17 is in centimeters, so we divide by 1,000 to convert into liters, and this one will give us 0.00017 moles. Determine the number of moles of hydrogen peroxide in 25 centimeters cube of solution E. 5 moles of hydrogen peroxide reacted with 2 moles of potassium permanganate. So remember, E is the one that reacted with D to give us the final products. So the ratio we have been given, that E, the ratio was 5 to 2. That's very nice now. So mole ratio E D, this is 5, this is 2, because we have been to remember, so hydrogen peroxide is E and potassium permanganate is D, 2 moles of D. So, but we know the number of moles of D. D, the number of moles is 0.00017. So we ask what will be the number of moles here. We use the ratio here. We say if 2 is equal to 0.00017, 5 will be what? So that is 5 times 0.00017. We divide by 2, and the number of moles of E in 25 is 0.000425 moles. This is the number of moles in E. These are the number of moles in E, 25 centimeters cube. Concentration in moles per liter of hydrogen peroxide. Concentration is in moles per liter simply means molality. Calculate the molality. The molality of a solution is called concentration in moles per liter. So there are 2 ways we can do that. Remember, a liter is 1,000 centimeters cube, that one you know. So let me remind you that concentration in moles per liter simply means molality of that solution. It is equal to molality. But we know now the number of moles of solution E in 25. What will be the number of moles in a liter? So we will say 0.0000425. These are the moles in 25 centimeters cube E, right? So concentration in moles, it is moles in 1 liter. Molality is the number of moles in a liter. So we will ask, a liter is 1,000 centimeters cube. Centimeters cube of E will contain how many moles? So that one is 1,000 times 0.000425. We divide by 25, and this one will give us 0.017. Capital M stands for molality. So that's one way. Or there is another way. You can use the formula, or you can draw this table here, this triangle of the table. Again, moles, molality, volume in liters. So what do we want this time around? We want molality. Molality is equal to, so you hold this, molality is equal to moles divided by volume in liters. So our moles is 0.0045. So for 0.00 0.0425. We divide by the volume of that solution. What was the volume of E that was used? It is 25. So 25 divided by 1,000, changing that into liters because this volume must be in liters. So by so doing, you will realize that the answer is going to be 0.017 capital M. That's another way you can do it. Determine the concentration in moles per liter of hydrogen peroxide in solution C. Very important. You need to understand that. Remember solution C, the solution E we have been using, we diluted it from C. We took 25 centimeters of C, diluted that C to form a 250 centimeters cube solution E, right? But it is the same hydrogen peroxide. The difference is the concentration and the number, the concentration. Remember now that moles, this is very important, moles of 250 centimeters cube solution E will be equal to number of moles in 25 centimeters cube solution C. Very important. Number of moles in 250 solution E will be exactly equal to the number of moles in 25 solution C. Remember tulichukua solution C 25 tukaweka kwa volumetric flask, tukadilute, tukatengeneza 250 centimeters cube, tukaita solution E. Kwa hivyo tukipata moles in 250 tunapata moles in 25 C. 250 E, 25 C. But we know the number of moles in E, 25. So 25 centimeters cube E equal to 0.0000425 moles. Right? So what will be the number of moles in 250? We will find 250 first of C, of E. This one will give us 250 times 0.0000425. We divide by 25. And the answer is going to be 0.00425 moles. So this is the number of moles in 250 centimeters cube solution E. But that number, this is the number of moles in 25. So this is the same number in 25 centimeters cube solution C, E, because moles does not change. So 0.00425, this will be the number of moles in 25 centimeters cube solution C. So we will ask 1,000 centimeters cube C will contain how many moles? So it is 1,000 times 0.00425 divided by 25. And this one will give us 0.17 capital M. So the molarity of the original solution C is 0.17 molar. So procedure 2, rinse the puree with solution E and then with distilled water. Fill the puree with solution C. Place 5 test tubes on a test tube rack and label them 1 to 5. To each test tube, place 10 centimeters cube of solution C from the puree. Clean the puree and fill it with solution B. Place 25 centimeters cube of solution B into a beaker. Using 100 ml measuring cylinder, add 25 centimeters cube of solution A to the container, to the beaker containing solution B. Pour the content of the test tube 1 to the mixture in the beaker immediately. Start the stopwatch. Swirl the content of the beaker and allow to stand. Record in the table 2. time in seconds taken for the blue color just up here. Measure the temperature of the final mixture and record in the place provided. So here you needed to, for students is required to just follow the instructions, and there's no big deal here. So after following instructions carefully, this is the table I have come up with. The final temperature in my was 27. Remember to use 1 decimal place for temperature, and time in seconds you can use 2 decimal places like I have used. Consistently, the table should be complete, and use the decimal places consistent for you to score all of the marks. So this is what you are supposed to put and complete the table, and then the rate of reaction is equal to 1000 over the inverse of time. So that's what we have done here. The inverse of this, the inverse of that 9 is this, like that. So we are going to use this data to draw the graph. So we are required to plot a graph of rate, this column here, against volume solution B. The volume of solution B here, this one. So that's what you are supposed to do. So on the y-axis, we should have rate. X-axis, we should have the volume of solution B. So you must label the x-axis and the y-axis. This one is rate, which is equal to 1000 divided by time inverse. That is a mark. And also this is the volume of solution B. That is a mark. After now doing this, we want to plot our graph using our data. So when B is 5, the rate is 12.5. So that's what we want to plot. The volume is 5, the rate should be 12. This is 10, 11, 12.5 here. That is where my point is. When the volume is 10, it is 13. 10, 13. So this is 12, 11, 10, 11, 12, 13 here. When the volume is 15, it gives us 15. 15, we have 15 here. When the volume is 20, the volume solution B is 20, it gives us 20 here. 20 is here. And when the volume is 25, it gives us 25.6. 25. That is 25, 26, 25.6. 25.6 would be, because this is 26, could be somewhere there, something like that. So remember, this is a rate. We expect that the line, it should be a straight line, and that straight line should pass through the origin. So it is you to see the points which will give you a line that will go pass through the origin when it is extended, right? So when you see this two, ujue kwamba hii line inafaa kupita kwa origin. Kwa hivyo unachukua zile points ambazo zinakupea the straight line yenye inaenda kwa origin. Hiyo ndio ilikuwa mark. So from here, if I extend this, it will give me here. This one will be, and then I will draw a line here. I will have a line there. But when this line is extended, it has to go, when it is extrapolated, it passes through the origin, like that. So that is what was expected for a student. So this is what would give you the marks that you needed. State why it was necessary to add distilled water to the mixture in the experiment. Why were we adding water? There are several answers for that. Answer number one is to decrease the concentration of the solution. This one, to decrease, is to lower. Somebody could say to lower the concentration. To vary the concentration. To vary is to change the concentration. Also, you can use here vary to lower the concentration. Any of them can work. To dilute the solution. To dilute the solution. So N can do. N of this can work. You are provided with solid F. Carry out the following test and record the observation and the inferences in the spaces provided. Describe the appearance of solid F. Solid F was ammonium ion 2 sulfate. Ammonium ion 2 sulfate appears pale green crystals. So you could simply write pale green crystals. Very green crystals. It is very green. But they allowed green crystals. So brown, like said, they just accepted those answers. But this is the most appropriate answer for that. Place about 1/3 of the solid F in a dry test tube. Heat it strongly. Heat the solid gently at the first and then strongly. Test any gas with red litmus and blue litmus paper. So we expected this. What happened? A colorless liquid is formed at the cooler parts of the test tube. For this one, it means that salt F contained the water of crystallization. Therefore, the answer should be F is hydrated salt, or solid F contains water of crystallization. Then what happened to the red litmus paper? Red litmus paper changed to blue, while blue litmus paper remains blue. So that means the gas that was produced, which changes red to blue, it means that gas is a basic. So it means ammonium ion is present. If you forget writing the ion, you can simply write basic gas present. So the correct way and the perfect one, the appropriate, is writing ammonium ion present, because we know ammonia gas is the only basic gas that will change red litmus paper to blue. So this is the correct way of presenting your answer. Place the remaining amount of solid F in a boiling tube. Add about 15 centimeters of distilled water and shake until it all dissolves. Use about 2 centimeters of portions of the solution in the test tube for test 1 to 4. Measure the pH of the first portion using a universal indicator, paper, and a chart. So here the pH was 5, 6. So they allowed the pH equal to 5, 4, or 6. That was the answer. So any student who could have written 5 or 4 or 6, the answer. What does that mean? When we have a pH of 5, 4, or 6, we know that is a very weak acid. So we simply write weakly acidic. And that is all. Weakly acidic. If the pH is 1, 2, and 3, you write strongly acidic, like that. If the pH is 8, 9, 10, then you write weakly alkaline, weakly basic. If it is 12, 13, 14, strongly basic. To the second portion, add aqueous sodium hydroxide dropwise until in excess. there, what we expected is, what happened is that the green precipitate was formed, which is insoluble in excess. A green precipitate formed that was insoluble in excess. Green precipitate insoluble in excess. That confirms if you have green, then you know that one is ion 2 ion present. Ion 2 ions are present. That's nice. To the third portion, add 3 drops of aqueous barium chloride, shake the mixture, and then add 1 centimeter of dilute hydrochloric acid. So here, a white precipitate was formed. But on adding barium chloride, a white PPT was formed. But after adding HCl, 1 centimeter HCl, the white precipitate did not dissolve. So that means inside there, we added barium, remember barium chloride, and formed a white precipitate. It means this barium entered into the solution and found a sulfate. It must have found a sulfate, a carbonate, a sulfite. Lazima ilikutana na hizi tatu and we form a white precipitate. But now when you add dilute sulfuric acid and the white precipitate does not dissolve, it means this one is not there, this one is not there. What is there is a sulfate, because a carbonate and a sulfite, when you add an acid, it dissolves to form a colorless solution. So a white precipitate is formed insoluble in dilute HCl. That confirms that it is the sulfate present. The sulfate present. The sulfate present. To the fourth portion, add about 3 centimeters of aqueous hydrogen peroxide, shake the mixture, and then add aqueous ammonia dropwise until next. So first, the green solution changes to brown. So if the green solution changes to brown, it means the ion 2 has been oxidized to ion 3. So you simply write here in the inference, ion 2 oxidized to ion 3, right? And then the brown precipitate, when on addition of the ammonia dropwise until in excess, a brown precipitate is formed which does not dissolve in excess. That confirms that ion 3 is present. Now, ion 3 is present. Fine. You are provided with an organic compound solid G. Carry out the following test and record the observation and inferences in the spaces provided. So you have been told it is an organic compound. Don't need to struggle. Place oral solid G in a boiling tube. Add 15 centimeters cube of distilled water and shake the mixture. Retain the mixture for use in B. So did the solid dissolve or it did not? So you need to tell us whether the solid dissolved or it didn't. But in this case, solid G dissolves to form a colorless solution. So if it does that, you should know that that solid is apolar. The key word is the polar. Solid G is polar. Or you simply write a polar organic compound present. Polar organic compound present. To about 2 centimeters portion of the mixture in the test tube, for each of the following tests, add sodium hydrogen carbonate. So whenever you are adding sodium hydrogen carbonate, you expect effervescence. So effervescence occurred. So effervescence occurs. If you don't write effervescence, you can write bubbles are formed or fizzing occurs. Fizzing occurs. Whenever fizzing occurs, it means this one iliingia hapo ndani ikapatana na and the organic acid, and we represent organic acids by R-COOH. These are organic, like ethanoic acid, propanoic acid. We represent them like this. So because we are in organic chemistry, let us just use this acid. Forget about this one. So you write RCr-COOH present. To the next portion, add acidified potassium permanganate. Remember this one is purple. So what will happen to the purple acidified potassium permanganate? Acidified potassium permanganate is decolorized. To decolorize, it means that the color changes from purple to colorless. And if that happens, then you should know the double bond, triple bond, and an alcohol is present. For acidified potassium permanganate purple, if it changes the color from purple to colorless, then an alkene, an alkyne, and an alcohol is present. And if it doesn't, they are absent. To the third portion, add 1 centimeter cube of acidified potassium permanganate. This one is orange. The color is orange. So what will happen to that? The orange acidified, and then there was warming. The orange acidified potassium dichromate changes to green on warming. So it changes to green. So immediately it changes to green, you should know what is present is the alcohol. So alcohol present, we use the general formula of alcohols, R-OH present, and you are done. So acidified potassium dichromate actually is used to test for alcohols. Once it changes from orange to green, then on warming, you know that it is alcohol that is present. I want to thank you for your time. Subscribe and share to your friends.